So welcome everyone to this edition of the Deep Space Dialogues about exploring distant exoplanet atmospheres with the James Webb Space Telescope. My name is Dr. Kelly Lipo, and I'm an education and outreach scientist at the Space Telescope Science Institute in Baltimore, Maryland. And tonight we're joined by Dr. Nestor Espinoza from the Space Telescope Science Institute. So I want to know where everyone is joining from. I'm really curious, so please let us know in the chat how this is going to work. We have a few questions prepared in advance, but we'll also be taking questions from the audience. So as we go along, feel free to drop your burning questions in the YouTube chat. And also a big thank you to Grant for moderating the chat for us tonight. And maybe we'll also see a little bit of him as we go along. Okay. So welcome, Nestor. Thanks for joining us tonight.
Thank you. Pleasure.
So could you let us know a little bit about yourself and maybe share a fun fact?
Sure, yeah. Well, my name is Nestor Espinoza. I'm an astronomer over here at the Space Telescope Science Institute. And my research focuses on exoplanets, on trying to find them. But lately, I've been really focused on how to characterize their atmospheres with this beautiful space telescope, James Webb. In terms of a fun fact, there's many. Let me choose two.
Okay.
First one is the first one is perhaps that I've played hockey basically all my life up until until like 6 to 7 years ago that I had to stop. But I want to come back to that. I even played against the national team of Australia once, and we won. They were very good. And the other fun fact is that I used to do a radio show back in Chile, where I come from, which was super fun. Like every week I would go for like 20 minutes to half an hour to just talk about astronomy, which was super fun.
So that is fun. I like doing radio. Okay, so my next question is, how did you get into astronomy and what did your career path look like?
Yeah, it's a very good question. Because when I was a little kid, I always liked space. And in fact, like mainly my mom really motivated this through like books and stuff like that I used to read. But it was never into my subconscious that I could actually become a scientist. I didn't knew that was a thing actually until I was like 15. Which my physics teacher just kind of grabbed me to side and told me like, hey, you have these bright eyes for astronomy. Whenever we speak about physics and astronomy, you do know that you can do this professionally, right? This was back in Chile. I didn't know this could even be done because in the movies, I typically see like, NASA people doing this kind of stuff. But then she convinced me this was a career path, and that's how I started. So I did my undergrad and my graduate studies back in Chile. So I got my PhD, and then I went for a fellowship in Germany for 2 years. And after that, I got this fantastic position here at Space Telescope where I get to do all this fun stuff with exoplanet science. It's been a very nice journey.
Really cool. Okay, so you said that you're an exoplanet scientist. I guess we can start off by just what is an exoplanet?
That's a hot topic. I say that's a hot topic because this was like the matter of discussion in the International Astronomical Union for many years. Like, what exactly is an exoplanet? The reality is that there's like a complex and very embedded definition. But for the conversation that we're having here, I think of an exoplanet as every bound object that has around like 10 times the mass of Jupiter and less. So anything like that it's orbiting a star other than the sun, to me, it's an exoplanet. So the name exoplanet means extrasolar planet, right? It's a planet that is orbiting outside a star different than the sun. And that's a key thing because, and that's an important distinction because from the definition of the International Astronomical Union, rogue planets, which we know they exist, like planets that are unbounded to stars, are like not exoplanets. But just between you and me and people that are here, let's just consider them planets too.
Okay. So things in the solar system don't count, like planets, but things orbiting other stars and maybe rogue planets also. They all kind of count as exoplanets. Okay.
All those little objects, they count. Yes.
Yeah. Okay. So how are exoplanets different than planets we have in our own solar system?
Well, that's actually kind of a key question of what we're doing with this exoplanet exploration. There's many motivating questions, but the one that is burning in my research, at least, is exactly this: how different are these other planets from the planets in the solar system? Right now, I mean, I cannot give you an exact answer because actually we don't know.
Mm.
But we have been exploring a wide diversity of worlds that were like beyond our wildest dreams, let's say. One of the things, just to give you an example, so one of the wildest examples that I have of this is that one of the things that really got me into astronomy was one time that my mom, I remember I was like 9 or something, that for some reason there was like Star Wars movies that were in the cinemas once again, and she brought me for a day to just watch this, right? And
Mm.
then in one, not to spoil anyone, but to do a spoiler here, but there's one particular planet, Tatooine, in which there's like 2 suns on the sky, right? And
Right.
that blew my mind. Like, does that make a lot of sense? And I remember asking my mom, and my mom was like, I don't know, that seems kind of made up. But then with the discoveries that we have made with exoplanets, we have found planets as weird as that one and weirder.
Mhm.
Planets orbiting multiple stars, planets orbiting stars which are different in color and size to the ones that we orbit here in the solar system. So it's a very weird, place out there, much more sci-fi than anything sci-fi we've written. But we still don't know exactly how weird we are. Like, is the solar system like a normal
Mm.
outcome of planet formation, for instance? That we're trying to figure out.
Yeah, because you would assume like that the solar system would be kind of a normal planetary system.
Mhm.
But that I think that's one thing that like as I've been following along as we've been discovering more and more exoplanets that maybe we're kind of the weirdos after all.
Could be, and actually, this has tricked us a lot in the history of exoplanet. Like, if we go back to the first discoveries of exoplanets,
Mhm.
the very first ones that orbited stars like the sun were actually pretty weird to our understanding of planets out there. So back in the day, I'm talking like in the early '90s and even in the late '80s, people were really looking for planets like the planets in the solar system out there. And in particular, the easiest to find are the giant planets orbiting other stars because they're more massive. They just,
Mhm.
make the biggest perturbation to try to detect them around other stars. And Jupiter and Saturn takes many, many years to orbit do a full orbit. So everyone was trying to follow up planets for a long periods of time, and it was very, very difficult. But the
Mhm.
very, very first planet orbiting a sun-like star, which was the one that got the Nobel Prize, actually orbited a star which in only a period of a few days. So that means if you were to go there in a rocket ship, you would celebrate New Year's every few years. It would be pretty fantastic, and you will need a lot of partying to happen in a few days, maybe too much.
Yeah.
Um, but that was a weird, very weird system, and that already broke all of our theories of how planets form, how planetary systems, get to where they get. So indeed, the jury is still out whether we are the weird ones or we are a commonality, at least around sun-like stars.
Yeah, here I'll put that this comment that we got from David. I just saw on the news today that we are at 6,000 exoplanets. So yeah, and we reached a milestone today. So that's really exciting. And I remember when I was told that we'd likely never be able to detect exoplanets, but here we are at 6,000.
Absolutely. I heard from some of the folks at the NASA Exoplanet Archive, which are the folks kind of that keep this count kind of almost officially, that they were celebrating and they even had a cake saying like 6,000. So yeah, it's a matter of celebration for sure.
Okay, cool. So that's like a little bit about exoplanets in general, but I guess what we're here to talk about is what we've been doing with Webb and exoplanets. So I guess my first question is, how do you, as an exoplanet scientist, or how do scientists in general use Webb to observe planets around other stars?
Yeah, Webb is such a fantastic and marvelous observatory. I first have to say that in the design of the James Webb Space Telescope, it was not made to do this kind of observation, right? It's thanks to the power of the engineering, the ingenuity of making such a stable observatory that we can use it for discoveries like the ones that we made in exoplanet science. And Webb, importantly, one of the main things that it does is to study in a lot of detail exoplanets that have already been discovered. So James Webb doesn't do a lot of new discoveries. There is a fraction of the time, around like 10 or 5% of the one that goes to exoplanets, that actually is trying to find new planets. But the vast majority of the time that James Webb uses for exoplanet science is to characterize in detail already known exoplanets.
Right.
And there's many techniques on how to do this. Webb, in fact, it's so stable and such a marvelous instrument that it's actually able to take like little photos even. They look like pixels indeed, but then you can actually take some of these images from nearby systems. But the vast majority of the atmospheric characterization, which is basically what Webb does the most, is done for transiting exoplanets. It's a special kind of planet that we are very lucky to have them aligned such that you can see them passing in front of the stars. Right. So I have a little video maybe that we can show up on what is this transiting exoplanet. So basically, if you have a planet like the one that you're seeing here, if you're lucky enough to be aligned through it, when the planet passes in front of the star, you can see this, there's like a light versus time plot. When the planet passes in front, it blocks part of the starlight, right? And then if you measure that blocking of that starlight kind of periodically, you basically have initially an exoplanet candidate, and then a lot of astronomers go and try to confirm that this is indeed a signal from a planet. But these transiting exoplanets are very special. And they are special because when the planets pass in front of their stars, there's another very marvelous thing that happens. So when the planets pass in front of their stars, the part of the atmosphere also blocks the star. So this is like the next little video that I have here. Mm-hmm. And if there's any atmosphere on the planet, then depending on the molecule that it's on the atmosphere, the planet will look bigger or smaller at different colors of light. So this is the wavelength that we're putting here. This is just our way of naming colors. So there's like this purple color, this green color, and this yellow color, right? So if the planet has an atmosphere for which there's an element that, for example, absorbs at these 2.3 microns in this example, it will look much bigger, right? And then that will create this like larger depth when the planet passes in front of the star. And we can actually use that to explore the atmospheric composition of distant exoplanets. So this is the main technique with which the James Webb Space Telescope is using to characterize atmospheres of planets, beyond our solar system.
Okay. So I guess one thing, like you were talking about when you were a kid, you were watching like science fiction movies. And I know whenever we put out a press release about a new exoplanet discovery, it always comes with like a nice illustration of what the planet could look like. Is that what your data looks like? Could we like resolve features on the surface of these planets?
That's a very good question. And the answer to that is like, no, we don't get to actually see images of these planets yet, like full-blown 3D, like these artistic impressions that we do. But we're able to tell a lot from this kind of data. Like we can say what kind of molecules there are in there, what kind of features and compositions these planets have, and so on. And in fact, maybe we can go and I can show you maybe a little bit of that data just to give people like a little taste of what is the kind of data that we actually see.
Okay, yeah.
So one of the planets that Webb studied first with this technique, it's an exoplanet that it's called WASP-39b. So WASP-39b, it's a planet that you will not want to go on vacation to. It's like very, very hot. And when you do like these kind of measurements, what we're trying to measure typically is something like this. So this is in the Y here, we have transit depth. And in the x-axis here, we have wavelength that you remember we mentioned that it was color. So the more to the right I'm going to plot points, the more it's to the red side of the house. And to the left here, it's the more to the blue side of the house. So before observing, we could observe this exoplanet before James Webb was up there. And the data that we had so far looked like this. So there's a fraction of data that was taken with HST, which is this HST UV optical side of the house.
Mm-hmm.
There was a little bit of infrared data there. And there were some points with Spitzer. So from these data points, it was actually, it's pretty hard to convince the public that there's something going on here. Although this was state of the art, and our models actually do very well on predicting that these features actually come from molecules. And here I've indicated some of them. So we knew that this planet has sodium, potassium, and this little feature of water at longer wavelengths. But then when we pointed our Webb to this planet, it looks like this. So now I don't need to convince you, right, that there's some wiggles happening, right? There's a lot of wiggles of water that I've indicated here in this plot. But the very cool feature is the one that is to the rightmost side of the screen, which is the CO2 feature here. So when we first saw this CO2, I almost fell from my chair, right? It was because it was so huge. And CO2 is a very important molecule. On giant planets, it's a way of telling how many metals there are. Just the more metals a giant planet has, the more elements heavier than hydrogen and helium, the more CO2 it has. So by eye, we could already tell that this was a very metal-rich planet. But the very important thing is that when you try to do science for smaller planets, like for rocky planets, CO2 is ubiquitous in the solar system. So you see it on Earth, you see it on Venus, you see it on Mars. So this is like a key feature of rocky exoplanets. And so the ability that Webb could do it, we did these observations very early in the game. The very fact that Webb could do this in like one shot was like, kind of a very, very good reminder that the precision that we're able to get with this it's far superior than what we could do before. So this kind of data is now routine. We get this kind of data for many planets. Like almost every week, we see a paper coming out with this kind of plots, and it's fantastic. It's just amazing.
Awesome. So one question that I got about this when I was talking about this on the weekend, and I think is a good question. So you'll see some of those have like multiple bumps from the same molecule. Why does the same molecule have more than one bump in that?
That's a fantastic question. This has to do, well, depending on the molecule and depending on the atom, this might be either due to different orbitals of the atoms, for instance, being excited in the planet atmosphere. So what's happening is the planet, it's kind of heating up these molecules, and then the electrons on these molecules kind of jumping orbitals, and then this is what this absorption happens here. But this might also come from vibration of the molecules as well, especially in the molecules because they vibrate, they kind of resonate within themselves. This actually opens a broad range of rays or colors of light that they like to eat. So basically, that's how typically I kind of try to explain how these absorption features happen. It's basically every molecule has its own diet. And the beautiful thing about this is that we know exactly which colors each molecule likes to eat. So when we don't see it, like in this case, like the planet seems to be eating some of that, then we know it's water at this, like in these wavelengths between 1 and 2 microns. And the one that it's at 4.5 microns, the one that I'm circling in this image, we know it's CO2 because we have observed it from lab experiments here on Earth. So it's a beautiful testament on how we can use the tools that we have here on Earth, which might seem like a very tiny planet in a very big universe, to make sense of the universe out there.
I mean, this continues to blow my mind, despite having like a PhD in astrophysics, that, we can take measurements on the ground here and then figure out what's in the atmosphere of this exoplanet that's like hundreds or thousands of light years away. It's amazing.
It is crazy. Yes, it is crazy that we can do this. It sounds, again, coming back to the argument of like science fiction, right?
Yeah.
This sounded very much like science fiction like 10, 15, 20 years ago. And in fact, I do know that the early proponents of this technique that I just presented here, which is transmission spectroscopy, I do know for a fact that for some of those people, some other researchers told them like, this is not going to work, right? Like this is like, with which telescope are you going to make this happen, right? But it worked. They were right, which is it's amazing. Yeah.
Okay. Here we have a question from the audience. I'll pull up here from Kevin. Similar to stars, are classifications being considered for any patterns seen in the types and layouts of exoplanets and exosystems?
Oh, what a good question. Yes. In fact, there's some not that old papers, like from 15, 20 years ago, that even before we started observing many of these atmospheres, we're predicting that they should fall in certain categories. As usual, nature has thrown all of that almost out of the window because planets are much more diverse than we believed they were in the past. But still, there's many people trying to figure out classification schemes for these planets, me included. Like a big part of the portfolio of research that I have, a big part of that is trying to make sense of trends in exoplanets, to try to understand their composition, their 3D-ness. So these are 3D objects, right? So different parts of the atmosphere might have different compositions. And in fact, last year we showed that this can be done with this very same technique with Webb, which is frankly quite amazing. I was also told the same thing when trying that other technique to prove the 3D-ness. Some people were like, yeah, you will never be able to do that. But then, Webb delivers very exquisite precision. So yes, people are thinking about patterns, thinking of classification schemes like the ones that are done for stars. But right now, it is very difficult to do that, at least with the data that we have, because planetary systems seem to be very, very complex objects. But I'm sure we'll figure it out. We just need, again, classic from a researcher, more data to figure those patterns out.
Of course, you always need more data. Here's another question from the chat. Do you actually see the exoplanet when you get the raw data from James Webb, or what does that look like?
That's a very good question. So for instance, for this technique, what you actually see is something like what I'm showing here, right? So it's like once you reduce the data a little bit. So I can, for instance, show you too how does like a transit event looks like. And it looks like something, I have a plot somewhere so I can show exactly what I mean by this. So there are some data sets for which you can actually see like a little point of light. So let me show you this one, for instance. So there are ways of extracting like images from planetary systems like this one. So this was an actually JWST observation very early in the JWST arena when the first data was released, basically, that you can actually see like an image of the planet. Because in this case, the planet is so well separated from the star, which is indicated in the bottom panels. You see that the star is indicated by a little white star. That blob that is down to the bottom left corner, that little bump, it's the planet, right? But it's like the shape that you're seeing, that it looks like a satellite. That's not really its shape. That's just because the Webb telescope produces like weird patterns on these images. So we can see it like in a bunch of pixels, like a little light, and you can see it in different colors, and the different colors tell you different amounts of information, as we just shared. So that's the kind of data that we get for when you're able to actually see an exoplanet. So we call them these direct imaged exoplanets. But for this transit data, the kind of plots that you typically see is something like this. So this is actually one of the first transit events that we saw with Webb. I had the privilege of producing this together with the beautiful team at the Office of Public Outreach in Space Telescope. I remember when we saw this data of this transit-like curve. So you remember I explained before, it's like whenever the planet sits outside, you see nothing, but when the planet passes in front, boop, you see a decrease in the flux as a function of time. The bottom here is time in Baltimore. So you see it was kind of very late at night. And I remember I woke up very early to figure out if this data were taken or not. It was during commissioning. So the data looks actually, when you explore the raw data products and you just try to add up the light that you receive from the data in Webb, this is how it looks like for the transiting exoplanets, which is, by the way, extremely beautiful.
Yeah.
Before Webb, it was very, very difficult to pull a signal like this right out of the raw data. So being able to see it like right off, it's fantastic.
Yeah, I mean, that was what amazed me seeing this for the first time. Like, this looks like a diagram where you're sort of outlining like what it should look like in theory, but that's it's like the raw data, well, basically the raw data out of the telescope.
Actually, funny story with this one is that we were preparing to observe this from like months in advance. So I have generated like simulations with like expected noise levels from Webb to extract this. And the first time I saw this plot, I thought I was pulling my simulations and not the real data. So I had to check like 3 times that I was not doing that. And I was amazed to see like it was like matched perfectly. So it's amazing.
Okay, that's awesome. Okay, so I guess why don't we move on a little bit, and maybe you could talk a little bit about, so you're talking about maybe classifying planets, and maybe we could roughly divide them into like gas giants like we have in our solar system, something like Jupiter, and rocky planets, something like Earth or Mercury. But we could start off with like gas giant planets. So what has Webb been learning about giant planets around other stars?
Well, that's an excellent question, because a lot of what we have learned a lot in the past 3 years, almost 4, is the fact that giant planets are very diverse objects. So the plot of the transmission spectrum that I showed before, like this, when I showed you the CO2 feature, that was indeed a giant planet. But it was kind of a giant planet, unlike what we see in the solar system, because it's a Jupiter-sized planet, but it has the mass of Saturn. So it's like very alien to, it's like a very puffy planet, right? And we're already observing, for instance, with these big CO2 features, that there's a wide diversity of metals that get into these planets. But really trying to figure out how that happens. But another thing that we've been uncovering on these exoplanets is that their chemistry is actually much more complicated than we simulated before these observations. To showcase you a little bit of that, let me bring back like that little plot that I showed, on which I was mentioning that we had this CO2 feature. I just did like a little inset into that feature. So I already showed you that big CO2 feature, and I already showed you that they also had this water feature that I'm indicating in this plot here. But you see here in the models, and if you look at the data, if I give you like a couple seconds, just inspect this data with your own eyes, you will see that these models don't fit a particular feature at 4 microns, right? I'm going to help you out a little bit here, which is this little bump here.
Okay.
This thing broke the minds of a lot of people that were looking at this data. So when we took this data, it was very early when we released the very first Webb data. And I remember there were many teams, our team included, trying to analyze and decipher what these data sets were telling us. And this little bump did not show up in any of the models that people were trying. Like, what is this? Is this a real thing or not?
Yeah.
We actually observed this with 2 instruments in 2 different observations, two different days, and the feature was still there. So it took a village, but we figured it out. And this thing, we now know is SO2, so it's sulfur dioxide.
Oh.
So this SO2 feature is not predicted by the models that were used to study this data at the very beginning, because this feature actually does not appear in a planet that is in isolation. So if we put a planet, on its own, you just heat it up. And remember, I told you this is a very hot planet. It's like 1500 kelvins. You don't want to go on vacation here. But if you heat up a planet like that and then you just heat it in isolation, this feature should not happen. But this planet, as I just mentioned before, is not in isolation. It is orbiting a star.
Right.
And what happens is that the UV radiation of that star is bombarding this atmosphere, and it's breaking a lot of some molecules in the planetary atmosphere. So we know that process of UV radiation breaking molecules, that is what we call photochemistry. And this is actually the first time ever that we're observing this in a planet outside the solar system, again, for a giant planet, right?
Yeah.
And there's a complex kind of chemical network, but basically all of this starts, if you see the water, it's there. So there's like a ray of light coming from like the middle top. So a ray of light coming into this water molecule, and that ray of light, which is UV light, kind of breaks this water molecule, and that starts like a little chain reaction that gets you down to this sulfur dioxide at the bottom right. This was a beautiful paper published by Chami Tsai in 2023, explaining this whole chemical network. It's such a beautiful paper to, because it's like that's the summary of what things happen there. But for people that are hearing this, that are very into chemistry or were very into chemistry in high school, you're gonna love this paper because it's one of this kind of tour de force, right? In which they just go trying to explain all the possible chemical networks, and they get to this one as the best explanation for that little bomb. So you see, Webb is really opening our eyes to chemistry that we had not the ability to explore outside the solar system, right? It's opening up this and many other possibilities for giant exoplanets. So that is a beautiful way of confirming both that we understand, that we're capable of understanding weird signals, right? We have the brain power, we have the people power. It was really an international effort. So if you look at the co-authors in that Chami Tsai's paper, there's people from everywhere, like chemists from all around the world trying to figure this out. And even some researchers, both here in the US and in Europe, saying like, oh yeah, this was maybe a possibility in a paper that I have like 15 years ago, right? So, it's really fantastic to see this kind of international collaboration happen, and the kind of science that we can extract, for giant planets like this one. It's been amazing.
Yeah, I bet that's a fun problem to work on if you're a chemist. Like, we found this weird thing in space. Can you explain it?
There's a screenshot somewhere of within the team. I cannot remember who it is. I think it was Natalie Battaglia herself, which was the PI of the program.
Mm-hmm.
She had like a whiteboard with all the possible molecules. It's just like a very crazy view of like no, and some mark that's like no, it can't be. So it was a blast to be part of that. Yeah.
Okay, awesome. Anything else on giant exoplanets?
Well, I think one of the things that we're trying to go really deep in with giant exoplanets is the fact that they, as I was just explaining before, they are really 3D objects, so three-dimensional objects.
Yeah.
And that's a beautiful prospect because that enables us to really explore with the precisions that we get with Webb. We're able to explore these planets in a detail that we had not before. And again, with this 3D-ness in mind. So these kind of precisions are just blowing our brains out in terms of like how deep, how precise you can be. And we're learning not only about the compositions, like the average composition, like what I just showed you,
right,
but also about how winds move in these exoplanets, or whether these planets are blowing off their atmosphere, some of them because they're too close to their stars. So there's a lot, like that's its own hour that I can just go on and on about results in this. It's
okay. Yeah. Well, okay. So maybe we'll try to get to another question we have here from the chat. Are typical observations of this type targeted at planets that transit often, like days, weeks to get the data, or is a single transit good enough to get a good signal?
That is an excellent question. So typically the transiting exoplanets that are easier to detect are the ones that have shorter orbital periods, right? It's just a matter of how we detect them. And then there's like a bias on detecting a lot of those. But in terms of observing it with Webb, these giant planets, in fact, their signatures are so big. There's these spectroscopic, like these features as a function of the different colors of light are so big that for most of them, you actually need just one observation to take, derive spectra like the one that I just showed you. And in fact, the ones that I have been showing you, like the last one that I showed you, it just comes from a single, basically, observation. You can already see this in glory detail.
Yeah.
So that's for the giant planets. But then if you go to the smaller and smaller planets, then you really need to build more observations, and you really need to take more and more. And maybe that's a good path to what rocky exoplanets.
Yeah, let's talk about rocky exoplanets.
How hard it is to explore them. Yeah, because for those ones, that is the same. It's the same technique. You're trying to extract these features from these planets, but then you really need to go deep in order to observe them. So maybe I can motivate the rocky exoplanet in some way. And what better way of motivating that than the solar system, right?
Okay.
So if I go to the solar system, and I have here like a little picture of like Mercury, Venus, and Earth. one way of approaching people that I like to tell people that I try to do in my day-to-day work exploring rocky exoplanets is that I'm very into solar system or planets as vacation destinations, basically.
Okay.
So if you look at the solar system planets, for instance, I have a rank system. And if you look at Mercury, like it's really an awful planet to go on vacation, right? It has very little to no atmosphere, depending who you ask.
Yeah.
And if you're in the day side or the night side, it's either too cold or too hot. Like you can cook a pizza or freeze a pizza in the same planet, which doesn't sound very nice.
Yeah.
The second one in my list is Venus. It's also awful. And for the other direction, right? You know how humans we're really like, we don't like too much or too little, right? Venus has too much atmosphere, which means it has so much atmosphere that if you were in the surface of Venus and you dare to bring your car would be splashed by the pressure in the surface because there's just too much atmosphere on top.
Yeah.
So don't bring your car to Venus. Okay. Very important to know. It's also too hot and cloudy because of the enormous greenhouse effect that it has on it. So these two ones have 0 star out of 5, as you can see here. But Mars has a star in my system.
Okay.
And I rate it as not great. The star is because it has some robots, and we like robots, right?
Yeah, everyone
and
likes
they're there doing hardcore science, right? And they are fantastic. And right now they are the biggest population on Mars. Mars, though, has little atmosphere, and that's problematic for us because we need a substantial atmosphere for everything that we need. You know, again, Venus versus Mars, like a lot of atmosphere Venus and little atmosphere Mars. But then, my favorite planet in this list is Earth, right? Earth is excellent. It's a nice atmosphere. You can meet your friends, and it has Wi-Fi. You can actually connect to the internet and watch this beautiful YouTube. So what I wanted to motivate with this is that just as I was explaining with giant planets in the diversity of atmospheres, this diversity in rocky planets also defines a lot of what you can do, right? For a planet like Mercury that doesn't have an atmosphere, well, you can study its surface, right? Because you can see it. For planets like Venus, Earth, and Mars, you already have a sample of planets that are very different. So Venus and Mars are dominated in carbon dioxide. Venus has a lot of carbon dioxide. Mars has like a tiny bit in comparison. But then Earth is like this nitrogen-dominated atmosphere. It's kind of weird, right? You have Venus CO2, Mars CO2. Maybe aliens out there that are looking at this are saying like, Venus has CO2, Mars CO2. Okay, your next observation of Earth must have CO2, right? And then bam, they find like it's nitrogen. It's like, what is going on in this system? So it's already pretty weird in the solar system, right? If you ask the planetary scientists to kind of tell you why this is, most of them will try to tell you like basically we have like not a lot of ideas on how they came up to be. It's like little changes during their formations or little changes during the chemistry, the history of these planets also, because this is also the atmosphere that you observe today.
Yeah.
These atmospheres have changed significantly since Earth was born to today. Even the atmosphere on Earth, there was a period back then when oxygen was blowing. It was huge on Earth, and we had these giant insects, right? For which there's like fossilized evidence and so on. So they change in time too. So this is a super exciting thing because might be wondering, well, can we explore these planets out there too? And the answer is that yes, we're actually doing a lot of exploration with Webb on these planets. Now, the interesting kind of twist, however, is that if you ask the average person out there, what do you think is the average star, or where do you think the average rocky planet lives around out there? The majority of people will answer like, a star like the sun, because that's the one we live in. But it turns out that the average star out there is not like the sun. It's actually a star that is actually much smaller than the sun. And here I brought like a little plot on like it's not a real image, right? Except for the sun. The sun one is a real image. Okay. But the other ones are artistic impressions of how stars look like. And actually the average star in our galaxy, it's actually small and red. Much smaller than the sun, like very tiny. Like you can see the comparison here, the size comparison. There's stars that are like the size of Jupiter, which is like completely crazy.
Yeah.
But this forms the vast majority of the stars, right? And the vast majority of rocky planets live around these stars too, as far as we know. The interesting bit is that because these stars are redder and smaller, That also means that if you want to feel the same temperature we feel here on Earth from a big star, imagine that your heater just suddenly shrinks. What you have to do is just get closer, right?
Right.
And this is in the next plot. It's a classic plot that we show in the x-axis here is the distance from the star of a planet to a star. And in the y-axis is the mass of the star. So we're looking at tiny red stars, which are the ones in the bottom. And the habitable zones, which are these zones in which if you are too close or too far away, it's not good if you have an atmosphere and you want to hold on to liquid water. But there's a particular distance to a star, which we call the habitable zone, which should really be called the zone at which, if you had an atmosphere, you might hold on to water, right?
Right. Yeah. It's not
that is what the habitable zone. Yes, exactly. We don't know if there's aliens on this thing. The habitable zone is just about the distance and whether if it has an atmosphere, it could hold on to liquid water. So that's a very interesting, very important zone for us. But then you see here that zone, it gets very, very close to the star. So you really have to be very close to these really tiny stars in order to make that happen. So that's actually a blessing for the transit method, because as I told you before, we observing planets that orbit very, very frequently. It's actually great because we can observe it with Webb many, many times during a year. But it's also a curse. And the curse comes from the fact that these stars might actually be active. And in fact, we know a lot of these red little stars, they're little but mighty. And they emit a lot of radiation out there. So much even that some models predict that maybe these planets must have their atmospheres stripped. So this is what this image here is illustrating basically on this. And that's actually a big part of the exploration that we're doing, trying to explore if these small rocky planets orbiting these small stars can hold on to their atmospheres. We call these small stars M dwarfs. And the big question that we're trying to answer with Webb right now is, can these M dwarfs, planets orbiting M dwarfs, can they hold on to the atmosphere given all this activity that they're blasted with?
Right. Yeah.
So yeah, that's a big question that we're trying to explore for a bunch of planets out there.
Yeah. Me and my grad school buddies used to get together, and we all were convinced that none of these planets will have atmospheres, but I'd like to be proven wrong.
Let's bet something against and for, right? So yeah.
Okay, great. So why don't we pull up a couple of questions for the chat, and then maybe we can talk about the TRAPPIST one. But before we do that, why don't we get to this? So how is JWST spectroscopy changing our understanding of exoplanet atmospheres, particularly around biosignatures or indications of habitability on Earth-like planets?
That's an excellent question. So we are trying to make big efforts into trying to explore habitable zone exoplanets. The reality of things is that it's very hard to find them, first of all, and we have a handful of those systems out there that are in these habitable zones that we're trying to explore with Webb. And I think the key capability that Webb has is its wide range of colors of light that it can get to. And I'm going to get to that. I think, yeah, you mentioned that maybe we can talk about TRAPPIST-1.
Right.
I'm going to mention that in a second. But maybe let's throw out another question before we go into that, because once you get me talking about TRAPPIST-1, you will have to stop me.
Okay, let's try one more question first. Then, so any methane on extrasolar?
Ooh. Okay, not on a rocky planet like the ones that we're talking about right now. But on giant planets, we have detected methane.
Oh.
And this is a very, very good question, because there was a methane problem for a long, long time. The methane problem for giant planets, it's a prediction by many theoretical investigators around the world that for colder than 1,000 kelvins, giant planets, we should observe methane. And the very first observations that we were getting is we were seeing an absence of methane. And everyone was kind of puzzled until the very first discovery came from our own Taylor Bell that works here at the Institute. So Taylor led a team in which they detected for the first time a methane feature on a giant exoplanet. And part of that solution had to do with the fact that planets are 3D. And because planets are 3D, there's some also vertical movements happening that might, prevent from this methane to actually show up. Maybe it gets hidden, or maybe other molecules are pulled up from the bottom of the atmosphere that kind of, shove that methane away. But for this particular exoplanet that he explored, they did find that methane. So yes, now I think I can think of a couple of examples on giant planets for which methane has been detected, but there's not on this detector for small rocky planets yet.
Okay, great. So let's talk about TRAPPIST-1.
TRAPPIST-1, okay. You want to do this?
Yes.
Let's do it.
Let's do it.
So TRAPPIST-1 is really kind of my favorite exoplanet system right now. It's the one I'm a bit obsessed with, to be very honest. And in this graphic that I wanted to show here, this is actually the cover of the Nature magazine when there was the discovery of TRAPPIST-1 was made. And I really love this image because it showcased this link between art and science super well. So the TRAPPIST-1 system is a system that it's as alien as it gets. So it's a system that is 40 light years away. So it means that if we threw a ray of light, it will take 40 years to get there. And it doesn't have 1, 2, 3, or 4 rocky planets orbiting the star. It has 7 rocky exoplanets. Let's start with the star. The star is as weird as it gets. It's the size of Jupiter. So
okay.
You heard that correctly. It's a star the size of Jupiter. It's very small. And then the planets are all packed up in these orbits. And the beautiful thing about this illustration is that it shows that planets that are too close, and they have names, so I'm going to put their little names here. B and C here, TRAPPIST-1b and TRAPPIST-1c. They're so close that if they had atmospheres, it will be too hot to sustain liquid water, so it will be in vapor form. And you do see in the image there that there's some vapor going on.
Yeah.
Now, look at TRAPPIST-1g and H. So there's like some little ice in the table, right? And that exemplifies the fact that if they had like an atmosphere, maybe it will be too cold for water to be in liquid form. It will be solidified. Then there's a bunch of them, D, E, and F, that are in this zone that we call the habitable zone, which is, again, as I explained before, is a distance to the star in which you're not too hot or too cold. And if you had an atmosphere, you could sustain liquid water on its surface. So one of the things that I'm trying to do with Webb is trying to figure out if they're good vacation destinations. And Webb is already telling us that TRAPPIST-1b, for instance, is not a very good vacation destination.
Oh, darn.
It's either like a bare rock or a very thin atmosphere that will be practically unbreathable. So if you're planning your next vacation to TRAPPIST-1, skip B.
Okay.
That's fine. TRAPPIST-1 also has this very, very alien concept that the orbits of these planets are all very, very next to each other.
Right.
And I brought here like a little comparison to the solar system, right? If I had like some kind of magic powers, right, and I could bring the TRAPPIST-1 system with all its planets to the solar system, all of them will fit well within the orbit of Mercury.
Wow.
So these planets are all very, very close together. This has many magical things. So I remember when this system got discovered, I met one of the discoverers, and we went out to have dinner, and then he was telling me that it was very, very hard to make sense of this system because they were so close. And in this discovery paper, one of the problems that they had is that the planets are so close to each other that if you try to simulate them, if you make a computer simulation,
right, and
you just put the planets like this, the gravity of the planets between them will just make them crash. So all their simulations were like the planets crashing.
Yeah.
And the argument then was like, so this system can't exist, right? It has to be something else. But then they discovered something. And that's the next thing that I want to show with a little video with some music. So if you like jazz, you're going to love this. Okay. Before we pull it up, let me explain a little bit what's going to happen. So this is a collaboration between artists and musicians in which they made music out of the orbits of the planets. And what that means, and we're going to show the video now, you're going to start hearing the sound in a little bit. What that means is that the period of the orbits and how they translate, because period translates to frequencies. These folks made the translation of those frequencies to audible notes. So if we put some play on this to start hearing this this video with this music, you're gonna start seeing the first planet of the system. There you go. It's gonna be a musical note. And then you're gonna hear the next one. And your brain is gonna start picking up a pattern. Try to listen to it with your musical ears. So if you go to the planets that are closer in, you see that the pitch starts going up. And that's because they go around more frequently, right? You need a higher note. We're almost getting there. We're in planet C. Next one's planet B. It's already something happening already musically. I want you to pay attention to the planets that are on the outside. Now what's going to happen is that we're going to add a drum when the farther away planet passes the other one. There you go. Now, there you go. And we're going to do that with all the planets. So this fantastic, by the way, mixture between science and music was made by systemsounds.com. They have actually created simulations like this one for many other systems that have this particularity. And the beautiful thing about this is that the reasoning behind why you're hearing this jazz-like music is because the orbits of the planets are not random. The periods of the planets are not random. They are in what we call a resonance. And actually, you remember the story that I was telling you about this person that participated in this team that discovered the system. Once they put in their computer simulations the exact periods of the planets in these particular, different musical notes, so to speak, in these particular frequencies, the system stayed forever, basically for many, many, many giga years, stable, we call them, that they didn't crash against each other. So it's this very fact that makes the system together. So we call that these planets are in resonance. Their orbits are in resonance with each other. It's like the orbits can talk with each other. And actually, from a planet formation perspective, this is a key signature of how we expect for disks on some systems to form these planets, right? They initially have a disk of material, and then these things start kind of condensing out in the planetary system to form these planets. And this showcases, it's like a very nice signature that these planets all form kind of together. Because if maybe you take a couple of them out, then the resonance might break, and then they might all clash against each other. So that's one of these fantastic things about this system, that it's in resonance. And the other thing that I wanted to share with everyone is the fact that these systems are so close together that this has sparked the imagination of a lot of people. This is an artist's rendition. This is not a real thing. But the other magical thing is that these planets are all so close together that if you could stand in the surface, in this case of TRAPPIST-1e, one of these planets in the habitable zone. So if you imagine that this could have an atmosphere, the planets are so close together that you will see them in the sky as like big moons.
Ooh.
So you could actually call your friend on TRAPPIST-1f, right, and tell them like, there's a storm coming your way, like just be careful, right, wear a coat and so on, which is pretty magical. Again, beyond science fiction, right? This is completely crazy.
If anyone out there is writing a science fiction novel, have a free
do it in TRAPPIST-1e. Exactly. Now, what we're trying to do with these systems is with this system, we're actually trying to figure out if there's an atmosphere in these planets or not. Right now, we don't know for the rest of the planet. For TRAPPIST-1b, we're mostly certain that it's possibly a piece of rock or a very thin planet. But we're actually making a good efforts to characterize the atmospheres, and that's what I wanted to share. This is a recent paper that we published last week, actually, on TRAPPIST-1e. And TRAPPIST-1e, we were able to figure out through two papers, to constrain a little bit the possibilities of the atmosphere. So if I bring the same plot that I brought before, and I put the possibilities that we had before seeing this data, is these three ones. So basically, maybe this planet could be made of a hydrogen-dominated atmosphere. Maybe it could be like Earth.
Okay.
Or maybe it could have no atmosphere.
Mm-hmm.
And we observed this, actually, the system. There was observations done before our observations with the Hubble Space Telescope, that as precise as the Hubble was, it was very difficult to tell, one of these models from the other.
Right.
But now with Webb, and I'm going to show next how the data with Webb looks like, we're able, to rule out this hydrogen-dominated one.
Right.
But this Earth-like atmosphere, or the no atmosphere, is still within the realm of possibilities.
Okay.
I just wanted to zoom in a little bit. The last thing that I'm going to mention about this one is that the y-axis tells you the error bars. And note that this is in parts per million. Maybe that doesn't ring a lot of bells, but just to give you an idea how difficult to make these measurements, this is like gathering all of Shakespeare's plays and just trying to find like 50 typos. That's the kind of precision that we're aiming for here. It's really, really precise. We don't know if this is an atmosphere like the Earth or not, but we have a follow-up program led by both grad student in my group, Natalie Allen, and myself. This was done with like 20 hours of observations, but now we're expanding that to like over 100 hours to figure out. So in the next few years, you're going to be hearing more from us on this. It's very exciting that we can do this, that we can actually ask these questions and have James Webb answer them with actual real data. It's crazy.
Okay, so stay tuned for that answer.
Yeah, exactly.
Okay, and we were discussing a habitable zone, and I think there's one good comment here that the habitable zone is only correct if life needs water to survive. So,
yeah, it's very Earth-centric, right?
Yeah, exactly. We only have one example to work from, so you got to use what you have.
That is exactly the case. Yes.
Yeah. Okay. So I guess maybe in our last couple of minutes, do you want to talk about what we can expect from Webb in the near future?
Yeah, I mean, Webb is doing a lot of explorations of rocky exoplanets. Again, we will need hours and hours to go through this, but there's, as well as we're trying to explore whether these planets have atmospheres or not, and how they compare to the atmospheres once we uncover them to the ones in the solar system. There's a lot of people doing, even like for the planets that don't have atmospheres, to try to figure out what the surfaces look like. Like you remember, we talked about like Mercury, we can explore the surface as well. We can indirectly explore the surfaces of planets out there too. And that is a very exciting part of what we're doing with rocky exoplanet science. But I just showed you the example of TRAPPIST-1e as like one exoplanet. But what about having more than that?
Right.
What about having like a sample of planets? And there's many different initiatives out there trying to do this with James Webb. And maybe one that I wanted to highlight was one that we're leading here at Space Telescope. I mean, the implementation at least, because this is really a community effort, which is the Rocky World's Director's Discretionary Time Program. So the exoplanet community got together a few years ago to try to figure out, what are the biggest questions that we should answer for exoplanet science. And one of the top ranked was atmospheres around these small M dwarfs. And the director from time to time at Space Telescope decides to use a big chunk of the time to answer big questions. So you all know the Hubble Deep Field, for instance, that was a director's discretionary time. The Frontier Fields, Ulysses, there have been many initiatives. And this is the next very big initiative that I have the privilege of leading with Hannah Diamond Loa over here at Space Telescope, the implementation of, because really this data is publicly available to everyone. And in fact, today, I have the privilege of saying that we mark a very big milestone, that we released the very first data set to the public domain of this program.
Yeah, I saw that today.
It's very exciting. It is very exciting. A huge milestone by a very, very nice team, both here at Space Telescope, but also with a lot of input from the community. And we're doing a sample, actually, of exploring 9 rocky worlds to try to figure out if they can have atmospheres or not. In this plot that I'm showing here, there's a line here that shows the cosmic shoreline. So the x-axis here is the escape velocity of all of these planets, which is basically how hard can they hold to their atmospheres.
Yeah.
And the y-axis is a measure of how much irradiation these planets have. And with this sample, we're exploring like all of this. And this cosmic shoreline divides basically the objects in the solar system that have atmosphere, which are in the bottom part of the plot, with the ones that don't, which is the top part of the plot. And with Rocky World, the sample that I'm showing here, we're exploring like the whole range, basically, to try to figure out, to try to make these detections. So to date, there's not a single rocky planet orbiting an M dwarf for which we have discovered evidence of an atmosphere, like strong evidence of an atmosphere. And this program and many others with Webb that are going to happen now and in the future, in a few years, are doing this big push. So I'm really excited for what's happening right now. So we're going from like a couple of targets. Now we're going into samples, which is super, super exciting. So I'm really pumped by this program.
Okay, yeah, this is exciting. And I guess maybe one last question from me, and then after that, maybe we can stay a little bit longer. I know we're at the top of the hour. Yeah. But when are we going to be able to sort of explore an exoplanet that's like our own Earth?
That's an excellent question too, because as I mentioned, with Webb, we can really explore planets that are orbiting these small M dwarfs, right? And then, yeah, your question is, okay, when we will be able to explore like a twin to our Earth?
Right, yeah.
Like the very first step, yeah, exactly.
Yeah.
Exactly. So the very first step there is discovering that twin Earth. So to date, we do not know of a single planet that has been detected at the same distance from the sun to the Earth out there around a sun-like star. So that has not happened yet. But I'm very, very hopeful that that's going to happen in the next, decade or so. But then once we discover that, the next big question is characterizing their atmospheres, right? I want to make my diagram. I want to know if that's a good vacation spot for you folks.
Exactly.
So to make that happen, we need another kind of observatory. We need an observatory that has new technology to really pull off, be able to differentiate the star from the planet. And there's already an idea on the mix right now, which is the Habitable Worlds Observatory. And the Habitable Worlds Observatory, the idea is to be able to actually take a little pictures of these systems, and not only pictures, but being able to extract the spectrum of these systems. This is a simulation from one of the mission concepts for the Habitable World Observatory, in which the idea is to do something like this, being able in another star to take these little pictures. And how we do that is through coronagraphy. So we're trying to block the light from the starlight. So we need to suppress that starlight to be able to see the planets outside of that. But to do that, we need a crazy starlight suppression. We need to suppress the starlight in 1 part to 10 billion. That sounds like, I don't know what you're talking about. Yeah. If you're into football, if you have been ever to like a Ravens stadium, this is like stabilizing every single hair on a full Ravens stadium game from space, right? That's very, very, very hard. But there's technology development happening that I'm sure we will figure out when we humans get together to plan this kind of stuff. It really pays off, and I'm really hopeful for that. So that's a matter of the future, answering your question. When we will be able to characterize like an Earth twin, we are planning that for the future, and Habitable Worlds would be able to do that. That's the idea.
Yeah. So when are we expecting Habitable Worlds to launch?
This is the idea is to plan launch from 2030, 2040, right? That's the range.
Okay.
And we are really hopeful for making that happen. Wouldn't it be exciting that in our lifetime we could get a picture like this of our cousin system out there? That sounds fantastic to me.
Okay, great. So maybe Grant, do you want to come in and join us? Do you have any other questions? You've been watching the chat?
We've had some good questions from chat so far. We've got a couple that I didn't manage to sneak in, so I want to put this one up first, back from the beginning of the program. Someone was commenting that this looks very similar to what they're running, and this kind of leads into a good question, which is, how is it that you are generating what we're seeing, what you're using to show us? Like, what sort of programs, what sort of background do you have? How is it that you're actually giving us the data that you're showing us?
That's a very good question. So we use a lot of computer software, and that's one of the things that I'm very proud of, particular of the Institute, that we build a lot of that software, not only between astronomers, but also with actual software engineers that know how to code 1,000 times better than I do. And it's this mix between these software development ideas and the scientific side of the house, this domain expertise and this technical expertise. Joining that is how these discoveries happen. So we use, in particular, a lot of the astronomical community is delving into Python scripting languages. So we write actual programs to reduce our data that are very particular for our science cases. but also within Space Telescope and also other places around the globe. We are publishing software that helps other scientists to do their science, right? So we use a lot of programming languages. We also like to explore the images directly. So we do a lot of image detection and image identification, which is super fun. And then once we do these beautiful plots that I'm showing here, I think it's very important to make the case that we do need this expertise on how to communicate this science as well. So that background is extremely important. And it's people like Kelly and yourself in which we rely on to really communicate effectively this science out there, both in terms of graphics, in terms of writing, and in terms of doing experiences like the ones that we're doing now. So it's a mixture of all of this. And I've learned a ton throughout my career. I keep learning with you folks here.
I do have other questions, but I did want to throw this up there. You had a couple of viewers from Chile come to say hi.
Hello, you see my natal Chile. Yes. Saludos para todos en Chile.
I thought you would enjoy that. Okay, so this is one that I hadn't heard, a term I hadn't heard before. How do you classify, or what do you call wandering planets?
No, not really. So some people call them rogue planets. It's up for grabs. I will call that. So yeah, I think rogue planets is the thing that has been popularized in science communication so far, I think, or wandering planets maybe. But yeah.
Gotcha. So here's another good one. To test against transit spectra models, have any observations been made from craft orbiting Mars or Jupiter or the inner planets?
That is an excellent question, and this makes me laugh because there's the grin really, because there's people that have wondered the same, and people that have tried to think about missions to make this happen. So doing this with the crafts that are orbiting Mars or other parts of the solar system, it's actually pretty hard because they are actually made not to observe the sun. Because these have very sensitive detectors that if you just point them to the sun, just like James Webb has its own sun shield. One of the most important things that James Webb cannot do, and this is programmed everywhere, is like, don't look at the sun, because the detectors will just go nuts. So it's very hard to do these kind of observations through the sun, to observe as if they were transiting exoplanets. Because of this, some people have actually thought about creating missions to do this, like specific missions to do these kind of observations in the solar system. Because I think the point of Kevin here is that we know how the spectra looks like. So there has been experiments like that. There is, however, one exception. And that exception, if I can recall correctly, it was the Cassini mission that observed a transit of like a self-transit, so to speak, of some moons and planets that we have used to validate some of these models. But it's like one case, and we want to do that hopefully for all the planets in the solar system. And there's some mission concepts have been built to try to do this, but they haven't been successful so far. But still, I think they are very important. So I agree with you, Kevin, that this is very, very important.
All right, and I have one last one that we will end on because I know we're a little past the hour now. How can people get updates when NASA finds new exoplanets, or what's the best way for them to get information when we send out releases or discover new things?
Well, we have our usual channels for figuring out new exoplanets that are discovered. So for new exoplanets that are discovered, my go-to typically is the NASA Exoplanet Archive. They keep the count, and there's like a lot of very expert people in the background. But in terms of web discoveries, Kelly, maybe you can share the usual channels that we use.
Yeah, so you can follow the Space Telescope Science Institute on all of the social media, your favorite social media platform, or nasa.gov/web to see the latest news from the telescope, including news about exoplanets.
Absolutely. And I'll end my questions there. So.
Okay, well, I guess that is the end of the program for tonight. So thank you everyone who joined us live, and thank you also to all of the people who are watching the recording of this in the future. So hi, future people. You're also welcome. Okay.
Thank you all for joining us. And as always, thank you for your good questions. It's because you guys are here that we get to continue doing these things. So don't forget to do the normal things like and share the video and whatnot, because that's how we gauge how well we do and get to keep doing what we're doing. So thank you, everyone in the audience, for commenting and participating and being here with us.
Yeah, and thanks, Nestor, for coming and answering our questions.
My pleasure. It was super fun. And yeah, just keep those questions coming. We will have even more for you to answer, for maybe some of you that are watching this, that you maybe can answer them in the future as well.
Okay.